your PhD, Chris, was about the formation of chert.
It was, yes.
So this is something that Chris has been interested in for very many years. Chert and Flint, of course, being essentially the same thing. He's a geochemist. Now, fortunately, Flint is made of quite a simple formula. It's silica. So perhaps we won't get too lost. I hope not. We shall see. Anyway, I'm sure it'll be really interesting. As I say, this is a subject close to Chris's heart. He's been working with the petrochemical industry, I think, mostly.
Yep.
So now he's retired, he can do the geology he's really interested in once more. So that's great. And I think with no more ado, I shall hand over to him for his...
Well, as you've heard, this was the subject of my PhD way back in 1984. I can just about remember the details now. Working on Flint also gives you a chance to work a lot with archaeologists. In fact, word spread around quite rapidly that, hey, there's a geologist that knows about Flint. So I had every man and his dog hammering at my door saying, can you look at these? Can you look at these? Why do I see this? Why do I see that? I'll introduce you to some of the characters from that study as we go along. Now, I'm sure everyone here is aware of Flints. You would have seen them on holiday, if not locally here. The sample on the left there was taken in Limburg near Maastricht. Sample on the right is from Seaford down in southern England. But the only place you won't see any flints is if you go to Flamborough Head in Yorkshire. And it's quite funny because a couple of years ago I was invited by the Yorkshire Geological Society to give a talk about flints to them. And I started off by saying, well, firstly, you haven't got flints here. And secondly, I've not even looked at a flint for about 40 years now. But it still went down quite well. Now, what are we going to talk about here? Well, how many of you enjoyed science at school? Okay, about 10% of you. Particularly chemistry. One or two, okay. Well, we're going to be covering quite a bit about chemistry as well as Flint, a fair bit of archaeology. I'll be talking a lot about chemistry and about bacteria, which we'll find out has a lot to do with how flints form. We'll take a slight detour here to discuss chemical redox behaviour. I'll explain that when we get there. We'll learn a little bit about how electron microscopes work. And we'll also touch on some nuclear physics, just for good measure. Don't panic, at least yet. It's all really quite simple. And if I explain it correctly, you should be able to follow every step. But really, don't panic just because you see nuclear physics and chemistry and bacteria on the screen. They're all straightforward, really. Oops, we're going backwards here. Right. Well, let's have a close look at a couple of flints. First one we're going to look at is a sample like this one from Brandon in Norfolk. It's where the famous Grimes Graves flint mines were located. prehistoric man used to go and dig very extensively around that area. And I'd taken a large lump of flint, which I'll talk about in more detail. But that's only part of the story. What we also have is, in a typical flint, is a number of these little white areas, which you can see in here, which I call the white bodies, for want of a better word, compared with the black flint. And if we go and have a look at the outside of the flint, what we typically see is there's an inner rim around the outside of the black flint. I call this the cortex, which it does say up there behind the Christmas decorations. A lot of archaeologists refer to this as the patina. I don't like the word patina because a true patina is a result of being handled. This is a result mostly of freshwater infiltration. But more critically, is just outside that white material, what we have is a thin layer around the very outside. It's missing from my specimens here, but it's a powdery white material, and it's composed largely of silicified chalk. If we go and have a close look at that, that will work now. These pictures were taken with an electron microscope. You can just about see the scale at the front there. It's just a few microns across, a few thousandths of a millimeter. But these particles are both parts of coccoliths. The thing on the left is called a rhabdolith. One on the right is a coccolith. Now, electron microscopes work by bombarding a rock sample or whatever with electrons, looking at the reflected light from those. But in doing so, they excite the atoms in there. And when the atoms get excited, they emit a certain wavelength of light. And the wavelength of light is characteristic of the chemistry of what you're looking at. So I looked at both of these samples, and everything you can see on the right there and on the left all gives a signature of silica, which is what the flint's made of. They're originally calcite from the chalk, so they've actually been replaced by silica in very, very fine detail. So the first lesson we should learn from this is that firstly, the flints are actually a replacement feature. So these stories you may have read about flints forming from meteorites and landing on Earth when the meteorite burnt up, and all the rest of the minerals like calcium got oxidized in the atmosphere and fell to Earth and blew into big sand dunes of calcium carbonate, like the South Downs, North Downs, Chilterns. So it's like, that's all rubbish. What we're looking at is originally chalk that's actually been the calcite replaced by silica. Now, if you want to study a rock, what the first thing a geologist does is to cut a thin section. Ideally, we polish the rock down until it's only about 30 thousandths of a millimetre thick, and then we can actually peer at it down the microscope and identify the minerals which are there. If we do that with flint, you finish up with this picture over on your left there. and what you find is you can't see much. There's a few white patches which are silicified fossils in there, but the background is just a hazy mass. And the problem there is the flint is made of very, very fine grains. They're just a few microns across. So if you've got a 30-meter thick section, you're looking at maybe 20 or so individual mineral grains stacked up. I did, as part of my research, try and grind some little wafer thin sections, and then you can start to see a bit more, but it doesn't help very much. But if you can't see much down an optical microscope, you have to go up a stage, and what we do is we go to the electron microscope. And now at a finer scale, this is the little scale bar there is 20,000th of a millimeter across. And you think, well, I can't see anything there much. Well, admittedly, it is difficult. But if you scrunch your eyes up a bit, you can just make out there are some little rounded forms in there sticking out the surface. So what I decided to do was take the flint and etch the surface with hydrofluoric acid. Now, hydrofluoric acid is great fun, but you've got to be rather careful in the lab. It reacts with your bones to give you fluorite bones, calcium fluoride bones. So you finish up with fingers with an octahedral cleavage, which isn't very nice. But as long as you keep it off your fingers, what it does is dissolve away the soft part of the silica, leaves the hardened material standing proud. And this is a sample of the same flint. It's actually a sample of this, the Brandon black flint here. And again, we're looking at the same scale as above. And now what you can see is, in this case, there's a foraminiferum just around here, which again has been silicified, been replaced. But a lot of this matrix is made of these little spherical lumps. Very tiny, and they're made of many, many grains themselves, but they're tiny little spherical silica lumps. Now, fortunately, we know quite a bit about those, because if you back out a bit, you can actually see it's the main component of the flint. But if we go to modern silica-rich sediments, like radiolarites and diatomites, what we find is a lot of these little things which form. And as you can see, these samples over on the left here, exactly the same scale as the ones in flint. And we refer to those as lepispheres. And they're composed of a mineral which we call opal CT. It's a bit of a cheat, really. It corresponds to mineral cristobalite if it's got a lattice defect in one direction, or the mineral tridymite if it's got a lattice defect in another direction. We don't bother arguing about that, we just call it opal CT. And these are essentially how we go from a normal siliceous organism through to a solid silica rock by dissolving the silica and precipitating these lepispheres. They're quite important to our story, as we'll see as I carry on. Now, diagenetic scheme that shows behind the tinsel there. What I'm going to do is introduce a little bit of microbiology. Oh, I'm going to talk first about the silica. Firstly, if you look over in the top left there, I've got opal A. This is an amorphous silica mineral. It comprises most radiolarians, most diatoms, spun spicules, a lot of other things in nature, including the spines on stinging nettles. So if you've ever got stung by a stinging nettle, which I think most of you will have done, that's where the silica spine is broken off in your hand. That's why it keeps itching for a long time, because you've got solid silica in the form of opal A in your hand. And with time, an increase in temperature, these things and various other bits eventually recrystallize to form the opal CT texture, such as I showed you previously. And then at a higher temperature, everything turns to quartz. It keeps the same structure, but it changes its chemical structure in terms of what's there. So all we find is normal quartz in most flints. If you go out to somewhere in, say, southern Limburg or parts of northern Belgium, you actually find some of the flints that are still made of this opal CT material. So we never got direct evidence that goes through that. In terms of formation, well, first we tend to find we get silicified fossils, such as this foraminiferan, little microscopic creature here. Then we get precipitation of a lot of these lithospheres, and then eventually in the little gaps that remain, which you can just see through here, we precipitate a very fine fibrous quartz or very fine fibrous silica in the form of chalcedony is what we call it, and this binds the whole lot together. And that is even finer grained than the rest of the flint. It's a little bit softer than the rest of the flint, which is rather important, as we'll see. So we've got this chalcedony binding together the lithospheres and the fossil fragments to give us three parts to the structure of a growth structure of a flint that's now made entirely of quartz, as you can see on the left there. So lesson 2 is not only are they replacement, but they formed initially as micropore filling lithospheres of opal CT that then became cemented together with this chalcedony, and that's the material which make up flint. I promise you a close look at flint. I bet no one's looked at them that close before. Now, what's important to our story here is that there is a lot of water in Flint, and the presence of water has been known for many years. As you can see there, God actually tells Moses that he brought forth water from the rock of Flint. We don't know quite who wrote Deuteronomy, but it is true there is water in Flint. The significance is it affects the workability of flint if you're making flint implements. It also affects the freezing behaviour of flints, which affected prehistoric man quite a bit. It also influences how the flint wears down when you use it for cutting trees or sharpening antlers and such like. And what we're going to do is take a detour into the world of archaeology to have a look at that in a moment. But where is this water located? Well, the raw structure of silica, SiO2, forms these little tetrahedral structures. These link up together through here. So each of these oxygen shares another oxygen either side of it. And the normal flint, that would leave a free oxygen bond sticking up into space on the edge of the crystal. And oxygen as a free bond doesn't like being sticking up in space unoccupied. So what happens is OH groups, if you have a look at the top one first, this is proving annoying. Little OH hydroxyl groups stick onto this oxygen and then cross-link between them. So we finish up with is what's called an anhydrous vicinal bond in there. What can then happen is we get additional water, hydrogen bonds onto the silica, onto the hydroxyl groups of the silica itself, and this gives us a fully hydrated surface. If you heat the flint up, we lose some of this water, and eventually we lose these OH groups, and these bonds join in what's called a silanol bond. So that's where the water occurs, as molecular water and as hydroxyl groups on the surface. Now, flint is very, very fine grained, and that means there's a very large surface area to have this water present. It may only be one molecule thick, as hydroxyl, but the surface area is immense. So there's quite a bit of water in the flint. And what can happen is if we recrystallize the flint a little bit, the diagram on the left there is a close look at this microfibrous chalcedony, and that's where most of the water is contained. But the reason it's in there, flint looks black, is because the microcrystalline structure completely scatters the light that goes into it. There's virtually no organic matter in the flint at all. It's just dispersal by light scattering. But what can happen is this chalcedony can recrystallize, and we finish up with this material on the right here, which you can see has got lots of microscopic pores in it. And what has happened there is we've gone from this structure on the left, we've lost the hydroxyl, which has gone to make these water-filled pores and left a more solid structure behind. These water-filled pores tend to reflect the light rather than total absorption of the light. So that is what you see when you have these white bodies, white patches on flint. It's just recrystallization to actually exsolve the water into microscopic fluid inclusions. Oh, there we go, you can see a picture of some there. That's these patches. Now, how do we actually know all this? I can see you thinking, well, we've got two main tools we can use in the laboratory. The first one is a technique called thermogravimetry. What we do is take some powdered flint in a little capsule, just a few milligrams, and then we heat the sample up and we weigh it to see the weight loss as a function of temperature. We can also use infrared spectroscopy, and that basically works by shining infrared light heat at the sample and then monitoring what the heat gets transmitted and what gets absorbed by the material. So we look at the thermogravimetry curve first. They're not very exciting. This actually shows, let's go back there. Ignore those for a moment. This just shows the weight loss and it just gives you a line. But what we can do is differentiate that curve so you can see the loss of individual components. This little jump there coincides with this spike is a result of weight loss due to the loss of carbon dioxide, as any carbonate in the sample breaks down. There's usually a few carbonate fragments in the flint that will break down at around about 600 to 700 degrees, and it gives rise to this spike. This very low temperature material we see here, that corresponds to essentially water within the flint sample, present as liquid water. And then the main part of interest is this loss here, and that's all the structure-bound water, which leaves at a much higher temperature than the surface water, and that is bound up to the flint crystal surfaces. Now the second technique, infrared, again what we do is take a salt, sodium chloride cell, little cube, we put our ground sample in that, and then we measure the transmittance of the light through different wavelengths of infrared. Now this little kink in there is isolated internal hydroxyl groups, the OH groups, which I showed you before. That little step in there corresponds with the so-called silanol bonds. That's the straight Si to oxygen bonds on the surface, which form as the sample ages. And this stuff in there is present to all the molecular water which is absorbed on the mineral surface. So that's the hydroxyl groups, which are these, and this is the water on the surface of the hydroxyl bound material, which is that one there. So we can actually see all this water being lost from thermogravimetry, and we can identify the chemical state of the water that's in there from the infrared spectrum. All quite sophisticated, really. Now, that's got a number of implications. Firstly is Stone Age man discovered how he could heat flints and actually improve the quality of the flint. The problem was that where we have a lot of lithospheres together, they're comparatively hard. If you fracture of flint, your fracture hits a little clump of lepospheres, the fracture shoots off in an unpredictable direction. Whereas if you cook the flint, it actually makes the internal structure of the flint a lot more homogeneous. So these are some experiments which I carried out with a whole host of co-authors here. David Griffiths, who's an archaeologist at the Institute of Archaeology in London, was the lead author of this paper. I'm in there too. Chris Bergman and funny Japanese name, Ohumu, were experimental flint knappers. They would take flints and create tools out of them, see what they're like. Don Robbins here was interested in his flint because he was developing the technique of thermoluminescence dating of flints. And Nigel Seeley is really there because he was head of department at the Institute of Archaeology and we didn't want to disappoint him. So a cast of a lot of us, we did think about adding U.T. Cobley et al. At the end of it, but I was overruled on that one. And the first stage of the experiments is our flint knappers carved out rough material, rough flakes, rather like this one. They just nap around the edges and we use those as the preforms. And then what we did is heat them up for I'm trying to go backwards here, but it won't let me. But never mind. What happens is that if we have untreated flints, the chalcedony is very soft compared with the lepospheres. So every time we hit a clump of lepospheres, everything diverts sideways. When we're pressure flaking, what we do is the archaeologist will sit down with one of these and a stick and then using pressure just flip off detailed flakes around the edge. And it's not very good with some samples, but heated flints, it becomes a lot better. Getting way ahead of myself here. Let me go back to where we were. That's better. So what we would do is take a sample of flint, rough it out. Then after heat treating, our archaeologists pair in here, Chris and Kiko, would actually go in and try and flake off bits. At first we gave them instructions, can you rate all these flints on a scale of 0 to 5 on how easy they are to pressure flake. They actually got back to us and said, can we use half scores? So essentially we said yes, which gave us a scale of 0 to 10 effectively of the flint. So we heated samples up for between 30 minutes and 24 hours and looked at the increase in quality of the flint, which on the left is a function of different temperatures. This is a sample of the Brandon flint, this material here, which was heated for just 1 hour at temperatures up to 350 or so. This is a flint from South Mimms in Oxfordshire that was heated for 24 hours. And if we combine all the results, you can actually see similar trends. If you're using a high temperature, the quality improves at a fairly low temperature and then decreases if you overheat it. Middle temperature, similar. If we only heat it for a short time, quality keeps getting better and better, and eventually this would also curve off at a higher temperature. So we know that time and temperature are important in how the flint is actually recrystallizing and releasing water, and how that affects the workability. The problem is Paleolithic man and woman didn't have thermostatically controlled ovens, and they didn't have digital watches either, so they clearly didn't use that method. So for stage 2, we decided we'd have to do as Stone Age man did and build a campfire. In fact, we built 3 campfires. At the back of the Institute of Archaeology in London, there's a small yard about the size of this room, and it's covered in loose soil and whatever. Right next door, there is the computer centre, who like having their windows open when it's hot, and they didn't like us very much because all our smoke was going straight through their windows. Smoke and computers don't mix very well, which gave Nigel Seeley something to do as head of department. He had to go and explain and say sorry, but we got away with it. So what we did, build 3 fires. One we just built on a solidish path that was there, starting with little twigs, getting bigger wood on top of it. Second one, we actually dug a hollow out of the soft soil and built our fire in there. And third one, we actually built a hearth around the fire to protect it from the wind. It was a very windy day that day. So we built a campfire. So we had these fires, and what we did is fill them full of flint blanks, samples like this thing here. And then some of the flints we put under the fire, some in the middle of the fire, some on the top of the fire, and we filled the fire with thermocouples so we could monitor the temperature that's going on. And then we gave them all to the archaeologists and said, there you go, sort that lot out, what's good, what's not. And a couple of days later, they came back and said, we've got some results for you. This lot are very good, this lot are rubbish, and such like. But it turned out that the best results was when you just take the flint blanks, go to your campfire, let the flames die down, and just rest them on the top and leave them to cook. Rest them on the hot embers, which makes sense. That's the simplest way of doing it as well. And we then had to leave them in the yard with instructions to the cleaners not to clear up after us. But it turned out this gave us quite a significant impact on the flint structure. What's happened essentially is this, in leprospheric flint is quite hard in comparison with interstitial chalcedony. When we homogenize the structure, the fracture would ignore these clusters of leprospheres and give you a much more predictable pattern. And the result of that is you can make very, very ornate artifacts. This is a Solutrean industry flint axe. It would have started with something like this, which you can see is very, very crude. But if you heat the flint and then pressure flake it, you can make this wonderful slow leaf, which is about so big. It's about so thick, really, really thin. We don't know what it was used for, of course. Probably had some ceremonial use. It was too thin to be much industrial use, but it certainly makes a hell of a difference. So now we know how Stonehenge man used to cook his flints. Second aspect we looked at was the effect of freezing, because it was very much observed that frozen flint tends to just fall apart in your hands. No use for making artifacts. So we sent a colleague of ours, Phil Harding. You may have seen Phil on the BBC Time Team programmes some years ago. Southern country accent man. He's exactly like he seems on television when you meet him. Very entertaining guy. But we sent him off out to collect a load of flints. We then got someone to cut them into cubes. They went to the British Museum, because Gail Sivking at the bottom there was director of the Stone Age Antiquities at the British Museum. And what we did was then, we meant to get Phil Harding to try and nap the flints after, but we couldn't wait. He was off filming something for television. So in the end, I just cracked them open. And what we found is that there was lots and lots of fractures in the flint. Now, interestingly, all these fractures were parallel in the flint samples. And we thought, what's happening there? Well, eventually I hit on the solution to that. If we start with a vertical fracture in the flint that's being held in by quite a weak stress laterally and quite a strong stress vertically. If you take the effect of both of those, that creates a weak point there, so this fracture will just grow vertically. But if you have no oblique microfracture forms, and then look at the effect of these two stresses, that actually gives you a weakness direction which will propagate near to the vertical. So you may start with a whole load of microfractures in the flint. As freezing continues, these all gradually curve to give exactly the same orientation, depending on where in the flint they are. So we finish up with a completely useless lump of flint. So essentially you finish up with flint that is absolutely no use whatsoever. The third aspect is microware polishers, and this is work I carried out with Rosemary Bradley, who's an absolutely charming young lady that was doing her PhD at the Institute of Archaeology at the same time I was doing my PhD, at King's College in London. And what she would look at is micro-wear polishes. What she would do is nap flints, get little flakes, and then she had the hard job. She would then get on her hands and knees in a cornfield and go around cutting corn down. Or she would get a bit of antler and try and clean up the antler with the flints. Or she would take a stone axe which she'd made and try and chop down a tree with it and have a look at the impact of this wear on the surface of the flint. Now these pictures you can see on the left, they don't mean much to me, but they actually show you edge-on view of some of these polishes which some of the flints gained. The problem is, whereas we looked at these and couldn't actually work out why some flints behave one way, other flints behave totally different. And the answer to that was quite straightforward. The lepospheres are quite hard, the interstitial calcity is soft. It depends what the microstructure of the flint flake is made of. Now that work is actually published way back in 1986, I think it was, 1983, in the proceedings of a big conference we held down in Brighton. And the first book there is now available as a reprint if any of you are particularly rich. It's about £45 paperback. You can get it on Amazon. The second one here is where we put the freezing experiments, and there's also a couple of other papers of mine in that one. That's about £80 if you're very rich and want to find out more. But both of those say available now on Amazon. So that's where to find out material. All that's very well, but it doesn't help us with how the flints formed in the first place. So the first question I'm going to look at is, where did the silica come from? Well, that's quite easy to answer, really. Well, to understand that, we need to know about the chemistry of silica. Now, I mentioned that biological organisms are made of opal A, which is quite soluble. It's gone behind the tinsel, I'm afraid. It's quite soluble in water. And then when it's in solution, we have silica solution. The solution tries to precipitate out either as quartz or as opal CT lepospheres. The problem is it can't. It needs something in there to speed the process up. Otherwise it just sits in metastable solution for millions and millions of years. So we need something to seed. Now we do know that opal A exists in the chalk, or existed in the chalk. Better. Because diatoms and radiolaria microfossils are composed of opal A, but we don't find any of those left in the chalk. They've clearly dissolved. Similarly, there's a whole load of sponges we find in the chalk. Sponge spicules are also made of opal A, but they're not preserved either. What we now find is a hollow due to this material in the flint. So clearly there was a lot of silica in the ocean water. All we need is something to cause this silica to seed as this opal CT. Well, you can do that experimentally. Turns out that if you go in the laboratory and you try to precipitate these opal lepospheres, the best way of doing it is by cations in the water, such as magnesium and calcium. Calcium, of course, there's a lot of in the chalk. Or you can dissolve extra carbonate in the water, and that will also seed precipitation of the opal CT lepospheres. Now, what I'm going to do is now have a look at some things called paramudras. Now these are remarkable flints. The one on the left there is from Quarry NC, just outside Maastricht. There's one big hill in Maastricht, and most of it's just a hole in the ground. What you can see there is this big columnar flint. I'll show you shortly, which over on the left there. There's a bigger one. A bigger one over here, big at the top, thin at the bottom. And these things just sit in the chalk in random places. You suddenly find these great big things, which are called paramudras.
How big are they, Chris?
Well,
What's the height of that thing?
that one's about 2 meters high. You can get them 3 meters. Or they can just be little mini mudras, we call them. But what's remarkable about these things is what we have is inside a cylindrical flint, we have a cemented chalk core, solid hard chalk, and in the very centre there we have a little animal burrow, a long thin animal burrow, and that is called, the burrow is called a Bathycnus paramudrae, to give it a scientific name. It was formed by a curious creature called a pognophore, which are little worm-like creatures, and they do nothing much. They just dig a little hole in the seafloor. The pognophores have no mouth, they have no anus. Everything goes on inside their bodies by absorption from the surrounding water. They just sort of sit there and do their thing, not disturbing anyone. But clearly, the presence of these pognophores in the middle of these structures is very important. Now, the other thing that's important is, let's go back to that one, is this central burrow also contains a lot of phosphate mineral, and it contains a lot of pyrite, although fool's gold, and a lot of a mineral called glauconite, which is green. That's useful for us because we know a lot about how pyrite forms, we know a lot about how glauconite forms, and we know a lot about how phosphate forms. And here we have flint and cemented chalk directly associated with those minerals. So if I can analyse what's in here, work out what the chemical environment was in here, that should actually help me quite a bit. Now, firstly, we've got to take a little diversion and talk about redox conditions. Redox, it stands for reduction oxidation. It's the opposite state. If there's lots of oxygen present, it's oxygenated. If there's no oxygen, it's reducing. And what we typically find is when we look at sediments, there is a crude vertical stratification, which is mediated by bacteria in the sediment. And what we find is near the surface, over up there, what we have is oxygenated seawater, and that oxygen diffuses into the sediment. And then a group of aerobic bacteria tend to use that oxygen to oxidize any organic matter. So gradually with depth, the oxygen gets depleted and runs out. Next, the bacteria are still in there. The bacteria go and use either nitrate, which contains oxygen, to oxidize organic matter, or some of them use iron or manganese oxides. Not important in the chalk, because the iron and manganese oxides that are introduced to the sediment are absorbed onto clays, and there's hardly any clay in the chalk. But gradually these become depleted as well. And then at greater depth, when there's no oxygen left, no iron oxides and no manganese oxides, the bacteria resort to the next best thing, which is sulfate. And what they do is take the oxygen from the sulfate to oxidize the organic matter. And that results in the formation of hydrogen sulfide, what an egg smell, and also releases bicarbonate species, which can lead to cementation by calcium carbonate. So in the centre of this Baffinus paramudri, clearly we've had a lot of sulfate reduction occurring locally where the paramudri is, but nowhere else. Now this redox behaviour can also affect individual elements, or strictly speaking, ions. So for example, iron, Fe, can exist in the reduced state as the 2-valent, 2+ iron, and that is soluble in water. If that's present in the sediment, it will just migrate away until it reaches oxygen, where it becomes oxidized to iron 3+, and it just precipitates, because this stuff is insoluble. Precipitates effectively as rust. Manganese is very similar, except there we're look at the species manganese 2+ and manganese 4+. The reduced manganese is very soluble. The oxidized manganese is insoluble. Again, it will migrate away and precipitate. There's a whole range of elements we could look at, but they're present in very low concentrations in the chalk, so it doesn't help us very much. So bear that one in mind, because what I'm going to talk about next is a paramudra I went and collected. So I thought, well, if we analyse what's in a paramudra, it should point out a bit more about what happens in Flint. The paramudra itself comes from a quarry up in Norfolk, at Caister. I had to go up on a Sunday because it's a working quarry. They don't like geologists in the way while they're quarrying. I had no idea who owned the quarry at that time until about 10 years later when I was at BP, and it turned out one of my colleagues there actually owned the quarry. If I'd have known that at the time, it would have been a lot easier. But what I did was went and collected one of these power movers, about so big. Not very helpful if you've got a little VW Beetle to carry it back in, which unfortunately my fellow geologist, Greta Mackenzie at the time had. She didn't want me to bring this back at all, but eventually I convinced her we'd have to do it. Then what I did was go and sample the cemented chalk core, and that's these samples you see through there. And then I got hold of the rock saw in the geology department at King's College and chopped a chunk out of flint. And that's actually here. I didn't pick the thinnest bit of flint because it blunts the rock saw. But then my friend Don Robbins, I mentioned before, had a little drill for drilling vertical samples. So I drilled a whole load of samples out of the flint, and I analysed chemically what happens in going from the centre here to the outside. Now, first something about clay minerals and dilution. If I start off growing a series of these lepospheres, that will actually I can go on to this next one. They will actually grow within the chalk, which has got a little bit of clay minerals. It's only about 1 or 2% of chalk is clay minerals, but that clay minerals are preserved within the flint. What I can then do is compact the flint around it, so I finish up with a lower concentration of clay minerals in the flint compared with the chalk. So all I need to do is go and analyse the amount of clay minerals in the flint compared with the surrounding chalk. And you can see that here. This is actually looking at dilution in the flint samples. Through here, here is the aluminium content of what's in the host chalk. Aluminium is an essential ingredient of clay minerals. When we come into the flint, we've actually got a lot less aluminium, and that's because it formed before the chalk compacted. So this variation from the host sediment to the flint, this dilution of aluminium or clay minerals, reflects the amount of compaction which has occurred in the flint since it formed. And what you'll notice here is a huge dilution. So clearly this happened during quite early diagenesis. And in fact, if you go to somewhere where you can see the bedding in the chalk, this sample from Yorkshire, what you can see is that we often see compaction around the solid flint, which shows you that there was solid flint there very early during diagenesis. Now, what about the cement in the core of the flint? Well, pyrite implies bacterial sulfate reduction, and this H2S, which goes on to form pyrite, but that reaction also releases a lot of bicarbonate, which will act to cement up the core. There's also glauconite present, and this contains iron in the oxidized and reduced state, so it's intermediate level before we reach sulfate reduction. And it contains calcium phosphate here, and the phosphorus probably coming from partly degradation of the pognophore and also partly decomposition of things like fish scales which are around in the area. But I know all of these are going on in the central chalk core. So what we can do is look at the chemistry of what's happening in this chalk core. And what we find is that magnesium increases slightly towards the central flint, so central pognophore burrow. This is the flint out here, and then decreases. This magnesium is present in the cement, and so from that, we don't want that one yet. So from that, we can actually work out how much cement was present there. And somewhere I have more chemistry I can show you. Okay, what we interpret this curve as, this is reflecting the cement core. So if I look at the aluminium content, where there's more cement, we have more dilution. So the original detrital aluminium must decrease towards the center there. So I can then work out what porosity the chalk was when it was cemented. If I go and measure the porosity of the chalk samples, well, it's around about 37% in the middle, decreasing to about 39% on the outside, and that means 47% of that sample in the center is cement, and about 39% of cemented chalk core is on the outside is a result of cement precipitating, making the chalk harder there. The fact you've got that, you can then translate that into the dilution effect, and that gives you the figures in here. That the initial porosity when it was being cemented, 60% over there, 79% over there. In other words, very, very high porosity chalk. It had only just been deposited. So whatever was happening near surface. Right. Now we need to learn a little bit of atomic physics. It's exciting for you. Well, a typical atom consists of a central nucleus here, which contains protons and neutrons and a few other exotic particles, and a sort of outside cloud which is occupied by electrons. These electrons have a negative charge. These protons have a positive charge. The numbers match, so an atom is typically electrically neutral. All very good. But the nucleus of carbon, say, contains 6 protons, and it has 6 electrons around the outside, and normally it has they don't contribute very much to the weight of an atom. Typically carbon will contain 6 neutrons, and the number of protons plus neutrons gives rise to the atomic weight of an element, and 6 plus 6 gives us an atomic weight of 12, which we signify with a superscript 12 and C for carbon, and that is called an isotope of carbon. It's still carbon, it's the same electron structure, has exactly the same chemical properties, but it just weighs a little bit more. So what we can do is go and measure this ratio. Some of the carbon has also got 2 extra neutrons, so it gives us carbon 14 there, and that is the radioactive isotope that decays with time. It's got a half-life of 1,550 something years. That's what we use for radiocarbon dating when we go and date remains in archaeology, for example. But that one's radioactive, but this carbon 13 and the normal carbon 12 are stable. And that means we don't lose any, we don't gain any. In fact, the amount of carbon 13 and carbon 12 on Earth is pretty much the same now as it was when the Earth formed. It's actually changed very slightly because some meteorites contain traces of carbon, but in the overall mass, that's relatively small. Now, we don't necessarily have to look just at carbon isotopes. We can also look at oxygen isotopes. We're interested in the oxygen of atomic weight 34 relative to 32. We can look at hydrogen isotopes, and there we're looking at the ratio hydrogen 2, which we call deuterium, to hydrogen 1, which we call protium. We can look at nitrogen isotopes if we want to, or we can look at sulfur isotopes, which we will do shortly. Now, these natural variations in the amount of carbon 13 relative to carbon 12 are really quite tiny. So what we have to do is compare the ratio in our sample with an internationally accepted standard material. And what we do for carbon is our international standard is one of these, which is a fossil belemnite. We call it the PDB standard because this belemnite comes from the Cretaceous of the Cretaceous PD formation in South Carolina. What was happening is Howard Urey, a physicist that first developed the dual inlet mass spectrometer measuring these ratios, was invited on a field trip by his friends from the geology department. And like all non-geologists, when faced with a big cliff of rock, what you do is you collect fossil belemnites. So he was in there, what can I use as a standard? And there on his filing cabinet, he had a big pile of belemnites. So, right, that'll do. And so internationally, one of these is now the standard. Obviously there's no sample left anymore, but we have secondary standards which we calibrate to PDB, and now all quoted carbon isotope values will be relative to PDB. And the variations difference from that in the ratio, only parts per thousand. So what we do is we compare with the standard, and our sample might be isotopically heavier, i.e. more carbon-13, or isotopically lighter, less carbon-13. And then to actually make it sensible numbers, we multiply the difference by 1,000. So we finish up with a PDB scale up here, which is relating to the belemnite. We refer to it as the C13 nomenclature, because it's a difference from our standard, and the units of that are parts per thousand. Parts per thousand signified with the 0 and then two zeros beneath the denominator. Percent would be 10, parts per thousand is 2. So the results I'll show you are quoted as parts per thousand deviation relative to this beast. So what? Well, when we actually look at a biochemical or a chemical reaction, all these different isotopes have the same reactivity because that's controlled by the electron cloud. But the heavy isotope, C13, reacts more slowly than the C12. It's rather like a race, like sports day at kids' school. You know, the little fat boy is always running behind because he's not as fast as the slim boy up ahead. And it's the same with these isotopes. And that gives rise to what's called isotope fractionation. And if we understand that, we understand a lot of chemical systems. It's used routinely in a lot of biomedical applications as well. Why am I telling you this? Well, we can use it. If we have a look at these stable isotopes in this cemented chalk core of the paramudra, this is where the flint will eventually form, this is the central burrow. What you can see is the isotopes of carbon, both in terms of carbon and indeed oxygen, become isotopically lighter towards the centre. And that's reflecting the source of the carbon which has contributed. These variations are very, very subtle. In practice, when we go and look at organic matter, Cretaceous organic matter, it has a value on the PDB scale of about -20 per mil, whereas the chalk itself has close to 0, about 2 per mil. So the net effect, we can say that most of this carbonate is actually chalk which has been redeposited. Only a small percentage of it, whereas about 6%, is coming from the decay of the organic matter itself. And that comes as a surprise. We were expecting to see very light isotopes there, but we don't. It's rather like if we have bacterial sulfate reduction attacking the organic matter, that's just tipping the balance. The bulk of the carbonate is coming from around the area, and probably from where we're dissolving carbonate to form the flint. There's also some problem in the host sediment out here, which is historically very light. I won't go into that. But what we can do now is some sums, calculations. Cement proportion, I showed you before, varies from about 42% close to the burrow down to about 38% of G. That's an average of about 40%. The chalk core itself, 7 centimeters radius, and that means the amount of cement over each centimetre of that burrow corresponds to 61.6 cubic centimetres, which in chemical terms is 1.07 moles, molecular weight in grams, times the amount. We know that about 6% of that comes from sulfate reduction. And if we look at the mass balance, that means we should generate about 1 mole of sulfide for every mole of sulfate that's in there. So what it means is there should be about 0.05 moles of sulfide present. Pyrite iron that's there is actually 0.01 moles. In other words, we've lost a lot of sulfide. Disappeared. It's not present. So where has this excess sulfide gone? Well, it must have migrated away from the central burrow, because that's where the sulfate reduction was occurring. And we know that as we go out, eventually we'll change from sulfate reducing conditions to oxygenated conditions as we move away. And when we actually reach oxygenated conditions, another group of bacteria will attack the H2S with oxygen and oxidize it back to the sulfate. That sulfate can then actually migrate back to the burrow, get used again, and the carbonate this releases in time will actually cause precipitation of silica. And we know we've got a lot of carbonate coming from dissolution of chalk where the flint forms. This is telling us that we should be precipitating flint in the same region. So the question is, where is this redox boundary between oxygenated conditions and reducing conditions? Well, we can use iron and manganese concentrations to tell that. Remember, both of these would exist in an oxidized state and in a reduced state. So we should find this redox boundary wherever we find peaks of the iron and manganese. Where do we find that? Well, this is a cemented chalk core, iron and manganese concentrations. These are flint samples. And what you can see is iron, this top one, great big peak, sample about 10 centimeters out from the core. Manganese, we get another peak a little bit further. So that means this flint, which is in green, was actually straddling the boundary between oxidizing and reducing conditions. rather like that. Now, when we actually get to this redox boundary, here is the reactions we get. It causes release of carbonate and calcium ions, and both of these concede precipitation of this silica from supersaturated solution. The reoxidized sulfate can then diffuse back to the burrow to produce more sulfide. It's what's called a reflux reaction. Meanwhile, the calcium and the bicarbonate released up here migrate towards the burrow where they add to the cementation. So, lesson 3, lesson 4, the flint is forming right around the boundary of oxidizing conditions and reducing conditions in the burrow. So essentially we've got our central bath thickness burrow in there. We've got oxygenated sediments all around it in there. We have sulfide moving out, being oxidized to sulfate, and then migrating back in again. And we have silica all around us, and that will precipitate where the carbonate is dissolving. Now, there will also be a lot of just dispersed organic matter in the sediment surrounding the chalk, and that will also eventually pass into sulfate reducing conditions. So while this is all oxidized, up here, there will be H2S forming down here, which means we have another boundary just through here where oxygenated conditions are juxtaposed with sulfate reducing conditions. So oxygen coming down, H2S going up. The result is we have a mixing zone in there, exactly the same as the paramudra, except it's a horizontal plane, and these two will actually mix in there, so that this will be a horizontal zone of flint formation as well. And that is exactly how this sample forms at the top. This is from Quarry NC, and what you can see is we have a paramudra sticking up at the top here, and when it comes to the bottom it forms a flint layer. No paramudra down here, and that flint is forming along with the flint in the paramudra here. So, can we test that? Well, yes, we can. Yep, okay. This is a very quick bit. Yes, we can. It'll come as no surprise that we can use our friends, the isotopes, again. What happens is when we get sulfate reduction, we get up to about 43 parts per thousand fractionation. Cretaceous seawater sulfate was about minus 16, plus 16 to plus 17 per mil. And that should give us H2S, which is around minus 27. and that will then migrate back to the burrow. So if I go and measure the sulfur isotopic ratio of the pyrite in the centre, if I see values that are less than minus 27 per mil, it proves that this sulfide-sulfate reflux is occurring. So I went and analysed some samples. I analysed 4 samples, 3 from the central burrow. You can see all of these are isotopically very, very light. In fact, they're so light, it can only possibly be caused by the sulfide-sulfate reflux mechanism. So, that's how they're forming. What controls the shape? Well, for the normal bedded flints, the shape will be controlled by whatever pathways the oxygen diffusing down and the H2S diffusing up became to be mixed. If you've got a burrow, normally the burrow infill is less compacted than the surrounding sediment. The mixing would occur within the burrow. This particular sample is reflected in the crustacean burrow. The whole burrow is about so big. And so we get a burrow-form flint. If we've got hardly any burrows, just a flat sediment, then sure enough we get a tabular flint, solid flint right across. And we find all intermediates in here. For example, this sample here, and this sample is part of one of these intermediate samples where we've had mixing within the burrow, but the flint has overgrown the burrow that's in there. And then just to complicate things, if we have isolated fossils have got organic matter in them, we get the same thing. So we find fossil sponges or fossil echinoids which are silicified. And if we've got early stage compaction joints in the chalk, that creates semi-vertical fractures, and that's a host of these diagonal sheet flints, which you can see running right across there. And where one of the flints meets the other, you can't actually see the boundary between them. They're forming at the same time. It's just because these fractures were mixing the oxygen and the sulfate. So, to conclude that, well, firstly, we'd seen that flints are a very early diagenetic replacement of the chalk. They formed in response to bacterial reactions, most notably the presence of hydrogen sulfide, H2S, and its reoxidation of excess H2S when we reach oxidative conditions that causes carbonate dissolution, and that in turn causes silica precipitation. Initially, we solidify some skeletal remains, but then we precipitate lots of these opal CT lepospheres, and then we actually cement chalcedony in the gaps that are left there afterwards. There's additional flints all around, many local organic concentration, and also in these big compaction joints that are in there too. Well, I said we'd have a close look.
That was a close look. Thank you very much, Chris. That was a close look at how Flint was formed and also at the various ways of discovering that is the case. So a lot of sort of chemistry going on in there to learn those what came out as being relatively simple lessons about formation of Flint. Any questions? Brian?
Going back to your introductory slide, I've been to Berlin Gap in the Cretaceous chalk, and the chert or flint is in horizontal lines pretty well, presumably following the bedding. Why is that?
That's because there's very little burrowing in the chalk, so that this oxygen sulfide boundary was very homogeneous.
Can you tell me what PDB meant?
PDB, can you tell us?
PDB is
Belemnite.
belemnite from the PD formation, South Carolina.
Neil?
What's the oldest known flint that you can definitely say was a flint tool, that you can definitely say was heated by fire?
It was appeared sometime during the Paleolithic, so we can't say a specific example, but the Paleolithic is spread quite rapidly.
Right. Well, that's amazing. Oh, another one. Yes.
Sorry. If you're putting flints on cinder beds, are they going to heat through evenly? And if they don't, couldn't that have an effect on how the napping works on the outside?
In theory, yes, but our nappers didn't notice any difference. They actually tried to push a flake right across the flint. So it's probably in there, but somewhere in those other bars I showed you.
Okay. Well, thank you very much.